My name is Libario Barbour, and today I'm gonna talk about Assignment 3 in Comp 3132 Deep Learning. This assignment is divided into two parts, Part A and Part B. Part A is about like the image convolution, how kernel mathematically works, and Part B is about building and training the convolutional neural network on the dataset. So let's talk about part A first. So part A is all about understanding convolution, and we're like using NumPy pure libraries, pure math. The idea is very simple: is that you take the image into you take a small grid of numbers called kernel, and you slide that kernel across every pixel of the image at every position. You multiply the kernel values with the pixel values underneath it, and you sum them all up. That sum becomes the new pixel value that position in the output image, and you can see the image depending on what number you put in the kernel. Let's see. First, we the first cell, we're just importing NumPy for array math. We're importing the PIL. We're importing like all kind of packages. Then here we're importing, like here in cell 2, 3, 4 in general. We use request.get. Here we get, so we can get the image URL. This sends HTTP request to the internet and gets the raw image data back. Then we print the response, and we put it in a variable called response. Then we convert those raw byte into NumPy array, and we pass the byte through byte.io. So image.open here, we can read them as if they were a file. Then we wrap the whole thing in NumPy array. The result is going to be like a 3D array with shape high with width by like 3 by 3. Like we can see, it's going to be like RGB, red, green, blue. Then here in cell 5, we display the image with plot.show, and it shows us the car in full color. Then we print the shape. The output is gonna like this output 140, 359 and 3. So the image is like 140 pixel tall, 359 pixel wide, and 3 color channels it has. We compare these 3 color channels to each other using this NumPy array underscore equal. And here in the output we see also false, false. The first one, it indicates that the red and green channels are not identical. And the second one, it says that the green and blue channel are also different. Here in cell number 7, we also display the 2D array as an image. We see that the image is yellow and green and purple instead of gray. This is because you call the imShow function on a 2D array without specifying the color. So Matplotlib library uses it. We use the default color, which is the yellow color, which maps low value to dark purple and high value to bright. In cell number 8, we visualize the value inside the resulting array. What does that mean? That means we select the entire 2D array, all the rows and all the column, to automatically be displayed. And then we go to the convolution with 2D kernel. In cell number 9, here in mp.pad input image array, here this adds a border of 0 around the image, 1 and 1. This one means 1 pixel of padding on each slide, like starting from top, bottom, left, right. This allows the 3 by 3 kernel to slide over every pixel, including the outermost edge and the corner pixel, without going out of the bound. Then kernel equals mp.array. This defines 3 by 3 identity kernel. Every weight is 0, except the corner, which is 1. This is like doing nothing to the kernel. Applying it produces an exact copy of the input. And then output underscore array equals mp.0. So this one here, it creates a blank of array of zeros with the same height and weight as the image. This is where the convolution result will be written pixel by pixel. And in cell number 10, we see the output original array shape, padded array shape. Padding added 2 to each dimension and 1 on each side. Height when from 140 to 142 and width from 359 to 361. This confirms that mp.pad works correctly. Then in cell number 11, we see this for loop. This loops over every row of original image. The -2 here accounts for the 1 minus pixel border added on each side, keeping the loop within valid bounds. And here we see the other loop, the inner loop. It loops over every column together. These two loops visit every single pixel position in the image. And here temp underscore array, this extracts the 3 by 3 patch of pixel from the padding image centered at position I and j, this position. Then we have the output underscore array writes the result into the output image at the correct position. In cell number 12, we plot the identity convolution output, and we see that the image looks identical to the original. Now rendered in true grayscale, black and white. This is exactly the expected result because the identity kernel keeps only the center pixel of each 3 by 3 patch and discard the rest. So every pixel in the output equals the same pixel in the input. Now cell number 13, we're going to define the function to trim the output value between 0 and 255. And so here we see define helper function that clips the single pixel value to the valid range between 0 and 255. If the value was less than 0, it returns 0, and that navigates, like this navigates value which happen when kernel weights are negative. It get clamped to 0, like that's pure black. If value less than 255 returns value, then the value already in range, or the ones that are left are unchanged. Else it returns 255, which happen when summing large positive weight get clamped to 255, so it's pure white. This is necessary because kernel with negative weight, like edge decators, can produce result outside the range between 0 and 255 pixel when doing the dot product with pixel intensities. So the output, this is just like function defined. Okay, so cell number 14. Also, we define function to apply convolution to the kernel to the image. Here we define a reusable convolutional function. It takes a 2D image and any kernel. Here the squish under pixels equals true, means pixel value are clamped to 0 to 255 by default. Padded underscore array equals mp.pad function pads the image with zeros exactly as before. Kernel with width underscore width equals kernel.shape at index 0 and kernel underscore height. These two reads the kernel dimension, so the function works with any size kernel. Here also in the line dedication in cell number 15, we see the render shows bright white streakers whenever horizontal edge exists in the original car image places, like the hood line, the roof line, window edges, bumpers. All these areas with no strong horizontal contrast appear dark near 0. Then we go to question. Based on the kernel present of the image above, here we see the same one.